Start now, I guess. Um, Paper is SF3D, stable fast 3D mesh reconstruction with UV unwrapping and Illumination disentanglement. This is a new paper by Stability AI, and essentially this allows for novel 3D content generation in under five in less than 50 milliseconds. It's based off their previous paper. If I could pull it up, Tripo SR. I think it's this one over here. No, that's the wrong one. Wow, everything up, going up over here. What's based on previous paper Tripo SR, which itself is, I won't say nearly identical, but is very closely related to LRM, large reconstruction model for a single image to 3D. Yeah, so let's get started. Okay, so the abstract. We present SF3D, a novel method for rapid and high quality textured mesh object for rapid and high quality textured object mesh reconstruction from a single image in just under 0.5 seconds. Unlike most existing approaches, SF3D is explicitly trained for mesh generation. So previous approaches, sometimes what they do is they'd instead train a signed distance field or isosurface or some other higher or lower level representation than what they actually want, which is the mesh. So incorporating a fast UV unwrapping technique that enables swift texture generation rather than relying on vertex colors. This method also learns to predict material parameters and normal maps to enhance the visual quality of the reconstructed 3D meshes. Furthermore, SF3D integrates a delighting step to effectively remove the low-frequency illumination effects, ensuring that the reconstructed meshes can be easily used in novel illumination environments. So these illumination effects they're talking about is that sometimes when we'd construct a mesh based off of some image that we have, the lighting effects are going to be baked in to their texture, into their UV map. And so this makes it that so if you want to dynamically light it or give it new lighting conditions, it doesn't look proper because you have parts that are more darkly colored than they should be because you haven't separated out the lighting from the actual color. So experiments demonstrate the superior performance of SF3D over existing techniques. Project page with model and code or code and model at HTTPS and the URL. Alright, introduction. High quality object meshes are essential for various use cases in movies, gaming, e-commerce, and AR/VR. In this work, we tackle the problem of generating high quality 3D object meshes from a single image. So this is single image reconstruction. This is a ill-posed and challenging problem, as this requires reasoning about the object's 3D shape and texture from only a single 2D projection, or in other words, image of that object. Single image object generation can simplify the tedious and manual object creation process. The quality of object mesh generation from a single image has dramatically improved in the past couple of years. With advances in transformer models, large synthetic data sets, and 3D aware image slash video generative models. Especially the transformer-based reconstruction models demonstrate phenomenal generalization capabilities on real-world images, despite being only trained on synthetic data sets, while also generating 3D assets from a single image in under 1 second. So here, what they're referring to is what's it called? What I was showing earlier, this LRM, as well as the work that Stability did, building on top of LRM about 4 months ago, Triple SR, which is very closely related. Just has some additional optimizations. Where was I? In under 1 second. Despite this rapid progress, several issues remain in these feed-forward fast 3D reconstruction models. These techniques often produce 3D assets that are not usable for downstream applications or require laborious manual post-processing. So, in other words, they're bad quality. Um, yeah. We identify several key issues in these techniques and propose a fast generation technique called stable fast 3D that generates higher quality and more usable 3D assets from single images while also retaining the fast generation speed within 0.5 seconds on a H100 GPU. Now, an H100 isn't yet consumer available, or isn't yet. It probably won't be consumer available. It still has quite a barrier to entry. You won't see this run on consumer cards. You'll Most people will either need to rent an H100 or it'll be left for bigger companies to use this as a service. But maybe in the future we'll see it used on consumer cards with future models. Next, we briefly introduce these issues and how we tackle those in SF3D. Light bake-in. Having shadows or other illumination effects in a given input image is common. Most existing works bake these effects into textures. So that's like what I was saying earlier, is that these lighting artifacts are baked straight in, right into the texture, and so it doesn't make it look proper under different lighting conditions, making the resulting 3D assets less usable. Having consistent lighting, in other words, homogeneous lighting or a lit or unlit character model at all angles. Having consistent lighting helps in easy integration into graphics pipelines. In SF3D, we propose decomposing the illumination and reflective properties by incorporating explicit illumination and differentiable shading models using spherical Gaussians. 1 second. For 3D Gaussians. Top row. The top row, in Figure 2, the top row shows us a sample result of SF3D, where the light bake-in is considerably reduced compared to the prior art. And so this is Tripo SR, you can see over here. This is the ground truth. With Tripo SR, you can see that there's dark light. The lighting doesn't look nearly as good as SF3D. And it looks to be that it has this lighting baked in. Yeah, and just generally SF3D seems to be performed, seems to have a better performance. So Vertex coloring. Another issue we found in most 3D generation models is that they produce meshes with a high vertex count. Using vertex coloring to represent object textures, this makes the resulting 3D assets inefficient to use in applications such as games. Oh, okay, right. So in games and movies and things like that, the high vertex count is not necessarily. I think it's linearly proportional to computation time, and so we often don't want a high vertex count. And so there are some ways to do through post processing. We're able to reduce the vertex count, but it'd be nicer if we could avoid that post processing step to begin with, as even just having it could add artifacts or make it look not nearly have as much quality as it could otherwise have. Using vertex coloring to represent the object texture, and yet for each vertex in these high poly meshes, they'll have a vertex color. And this vertex color basically it determines the coloring of your mesh. So say you have a triangle that has 3 vertices. Every vertice will have an associated vertex color, and then to get the color of that mesh face, it'll interpolate between the 3 vertices. And having to do that for 10 let's say 10 times as many meshes as you need to will take is an inefficiency that could otherwise be solved for. Where was I at? What the hell? I lost. Where was that? Right. This makes the resulting 3D assets inefficient to use in applications such as games. A key issue is the additional processing time of UV unwrapping, which can take longer than the entire object generation. So UV unwrapping is having an object and projecting its colors to some other space. So you're unwrapping the color of a 3D object into a 2D map, and that takes a lot of processing power or processing time, which can take longer than the entire object generation itself. For example, Xatlas and Geogram can take up to 30 seconds or 10 seconds for a single asset, respectively. To tackle this, they propose a highly parallelizable, fast box projection-based UV unwrapping technique, which we'll get into later, to achieve a 0.5 second generation time. This effect of relying on vertex coloring versus UV unwrapping can be seen in Figure 2. In Figure 2, middle row, where Trico SR captures fewer details than SF3D, despite requiring 10 times the polygon count. So we can see over here, middle row, that their coloring algorithm or technique causes far lower quality than to the ones to the right, which is SF3D, while SF3D uses 10 times less the polygon count, which is a pretty impressive feat that I managed to do. The effect of relying on okay, so this is where we're at. Marching cubes artifacts. The feed-forward networks often create volumetric representations, such as triplane nerves, which we'll get into later, which are converted to meshes using the marching cubes algorithm. Marching cubes can cause stair-stepping artifacts. So basically, you can think of it as jaggedy edges, which can be somewhat reduced by increasing the volume resolution. So if you increase the resolution that marching cubes is being applied on, these jagged edges could get smoother since you just have more of them. Yeah. So, however, this comes at the large cost of computational overhead. So the larger resolution you have, it with marching cubes, it gets longer quadratically. In contrast, SF3D uses more efficient architecture for higher resolution triplanes, and also produces meshes using dmtet. So that's deep marching tetrahedra, which I'll get into in just a moment, with learned vertex displacement and normal maps, resulting in smoother mesh surfaces. Figure 2 demonstrates the smoothness of the SF3D mesh compared to that of Trico SR. Figure 2. So you could see, if I zoom in, that like in this third row, the plant under Trico SR has a lot of these jaggedy edges. It's indenting downwards and indenting up, while SF3D, their technique, results in a smooth surface, and they're using even less polygons. So, for DM tetrahedra, or deep marching tetrahedra, I have the paper right over here. No, that's the wrong one again. dmtet. So deep marching tetrahedra, instead of using a nerf or some representation of a sign distance field, SDF, what they do is they encode a sign distance field in a grid of tetrahedra. So you could think of each tetrahedra telling you whether it's inside or outside this isosurface. And also with this demarching tetrahedra, the isosurface is is deformable, so you could split a tetrahedra into two in places that you need a high resolution or there's high frequency details. The tetrahedra will divide to fit the resolution needed, and also demarching tetrahedra is differentiable. So you could train through demarching tetrahedras and affect your mesh directly. Because demarching tetrahedra has a way of getting from this tetrahedral grid directly to your mesh. And so what's it called, backpropagate through that mesh back to your input, then you don't have to train on a higher or lower level representation, such as an isosurface, and you could train directly on your mesh reconstruction. Right. So, somewhat reduced. dmtet. Okay. So lack of material properties. The generation from previous feed-forward techniques often look dull when they are rendered using different illuminations. This is mainly due to the lack of explicit material properties in the output generation, which can influence the light reflection. To tackle this, we predict non-spatially varying material properties. So material properties tell you the roughness, metallicness of an object, and many times it's not distributed evenly across an object, and that a group of faces of your object will have a different material than another group of faces. And what they do is they predict a single material or a single set of materials that applies across every face of your object. This addition, sorry, one second. All right. This addition is apparent when rendering different generated objects in Figure 2, bottom row. So you can see over here, in this bottom row here, if I zoom in, their constructions of, for example, a toaster has zero reflection to it. Well, for SF3D, you can see that there's some like glare and some it has some metallicness to it that you don't have with TripOSR. And it also has roughness and other. I believe they use roughness and metallicness. I think those are the only two material properties that they affect. But you could especially see it on this toaster, how there's a higher metallicness with the toaster using SF3D as opposed to TripOSR, the predecessor paper. Okay, and yeah, so as I was saying earlier, they predict non-spatially varying material properties, in that the entire object will have the same material properties. This addition is apparent when rendering different generated objects in Figure 2, bottom row. That's what I just went over. With these advances, SF3D can generate high-quality 3D meshes from a single image with several desirable properties for downstream applications on both shapes, low polygon yet smooth, and textures. Illumination disentangled UV maps with material properties. This illumination disentangled UV maps just means that they have their UV maps of color disentangled from the light effects, and so there are no light artifacts within their texture. The 3D assets are small in size, under 1 megabyte, and can be created in 0.5 seconds for text to 3D mesh generation. A fast text to image can be combined with SF3D to produce meshes in about 1 second. So again, SF3D, it takes a single image to produce a mesh, and so it's not a text to 3D object model, but it's a single image to object generation model. But you can easily make a quasi text to object by just using a text generation model first, and taking the output of your text to image and taking that text to image into your image to object. So experimental results demonstrate higher quality results with SF3D compared to existing works, In short, SF3D provides a comprehensive technique for fast, high-quality 3D object generation from single images, addressing both speed and usability in practical applications. All right, any questions? Lag? Let's see what's going on. Okay, OBS shows it's fine. Someone's saying lag. From the people watching, do you guys have lag with this? Is this lagging for you? Okay. All right. It seems to be back. Okay. So, I mean, I guess if there's no question, we'll move on to no questions. We'll move on to related work. I'll just take a drink. So, related work: 3D reconstruction using image generative priors. Diffusion models have proven to be powerful generative models for various tasks. Several works, such as 0123 and others, leverage the object priors in these diffusion models by adapting their generative models for 3D generation. Score distillation sampling is often used to optimize 3D representations using the 2D diffusion models. However, it was found that relying solely on the image prior does not always produce consistent multi-view results. So just in case if you're not familiar, which you probably would be if you're watching the stream, the way that object reconstruction is done a lot of the time is not by having a straight MLP using using like raw data from a 3D data set like Observerse, but instead you'll try and use our 2D diffusion models, which you have a lot of data for that we don't have a lot of data for 3D models. We use a 2D model and compare our rendering of a theoretical object that we have in 2D, these images, and try and make it so that our actual object, when rendered, has the same output as our already created image in our diffusion model. So a diffusion model has one rendering of our image from a specific angle, and if our actual object produces the same image when rendered from that same angle, then it has a loss. And you're trying to minimize that loss. That's how score distillation sampling works in a nutshell. However, it was found that relying solely on the image prior does not always produce consistent multi-view results. This issue is improved in follow-up works by simultaneously generating multiple views of an object. So instead of having a single image or having a diffusion model that produces a single image from, let's say, the front, you'll have a diffusion model that produces an image from the front and is also conditioned to generate an image from multiple different angles. So let's say the back, like some angle on the side, and many of these use upwards of like 50 images, while this paper and some other models only use a single image. So this issue is improved in follow-up works by simultaneously generating multiple views of an object. Another approach is to explicitly introduce 3D awareness, or use a multi-view diffusion process to generate 3D objects. While diffusion models can generate videos or multi-view images relatively quickly, they require a 3D reconstruction step to create 3D meshes from a single image. Even with fast techniques, generating an object can still take several minutes. Our work focuses on fast generation speeds in 0.5 seconds for image to 3D. Feed-forward 3D reconstruction. Recently, LRM, which is the paper that I was showing earlier, let me bring it up again for a second. This is LRM. Recently, LRM and the follow-up works demonstrated that the fast and reliable 3D generation is possible using feed-forward networks trained on large synthetic data sets. So this is on large data sets of 3D models that people might have made in Blender or other sculpting software. These works use a large transformer model to directly predict triplanes as the volume representation, which can then be ray-marched using NeRF. I'll explain this a little bit more in depth shortly. This allows these models to train on multi-view data sets, as only the rendering loss is required for training. A set of follow-up works addressed to remedy the reliance on multi-view data sets. This can produce meshes from images in seconds compared to the generative prior-based approaches. So this large transformer model to predict triplanes as the volume representation they're referring to this over here, where you can have an image, or how they do it is you'll have your image, and they first put that through a convolutional so they have this image and they put it into a transformer network, into a vision transformer, and I won't get into too much detail, but with this vision transformer they then apply some learnable position embeddings, and they use cross attention with that learnable position embedding and some camera intrinsic and extrinsic parameters, and eventually you get to this triplane representation, and that triplane representation could eventually be converted into a mesh. This isn't too important because you should read it. It's a good read, but the paper that we're going over diverges quite a bit from this. So this allows these models to train on. We already read this. Okay. Several follow-up works emerged which use Gaussian splatting as the representation, or directly integrate a mesh prediction. Another group of methods integrates diffusion models with the feed-forward models by either directly generating the triplanes using LRM as the denoiser, or using it as the conditioning. As single image reconstruction is a challenging task, several models leverage the extensive prior of multi-view diffusion models to generate multiple views of an object, which the feed-forward model can uses to produce a 3D output. So this is somewhat similar to what I was talking about earlier. Generally, these models can learn the scene's radiance, meaning lighting information is baked into the objects. LDM tries to remedy this by learning an additional shading color to capture the shading information. However, training requires having access to the ground truth albedo color. Albedo color is just the color of your object with zero lighting on it at all. So either the unlit or fully lit object as a supervision signal. Compared to LDM, our method also learns an Illumination model, enabling training on regular multi-view data sets. And we predict more material properties, and they also predict more material properties. We also tackle fast UV unwrapping. So unlike previous works, we do not have to rely on vertex colors while keeping the 3D generation time short. So these vertex colors, as I was saying earlier, each mesh is made, each mesh is made by a set of vertices, and each face connects these vertices. And so to get the color of a face, what's traditionally done is, or what's still done, is you'll have a UV color or a vertex color associated with each vertex, and the face color is an interpolation of those vertex colors, while keeping the 3D generation time short. Material decomposition. Predicting only the radiance of an object has the downside that relighting does not produce convincing results. Current works in single scene optimization are often based on NeRF or Gaussian splatting, and decompose multiple input images, greater than 50, into light and materials. These methods often predict material properties of a physically based rendering shading model. A few recent works tackle joint 3D shape and material generation, such as UniDream or Fantasia 3D. I haven't read these yet. I was planning on reading Fantasia 3D soon. I might do that on stream. But that's kind of an older paper. By optimizing the material properties using a SDS loss. However, that's the score distillation sampling, which lets you backpropagate or lets you use a rendering of your model compared to the ground truth as your loss. However, this optimization takes several hours to converge. Another set of work aims to. Our work generates a textured object with homogeneous material properties from a single image under natural illumination at fast generation speeds. So that's what I was talking about earlier. They'll generate a set of material properties for an entire object. Method. Alright, we propose SF3D, which converts a single object image into a textured and UV unwrapped 3D model with delit, albedo, and material properties. As explained in the introduction section, with SF3D, we aim to fix the issues shown in Figure 2 and introduce additional quality enhancements. So this is just a summary of the abstract. Preliminaries. Our work is based on TripoSR, which trains a large transformer-based network that outputs a triplane-based 3D representation from a single image. TripoSR is trained with multi-view image datasets without explicit 3D supervision. So that means that unlike this, where they're using the demarching tetrahedra that I was talking about earlier, they do not perform they don't backpropagate directly through the mesh itself. So they can't just as I was saying, they don't backpropagate through your mesh itself. Instead, they're using some higher or lower level representation, which is not exactly the thing that they're trying to optimize. In TripoSR, the image is encoded using Dino. So this is just like if you guys are familiar with Clip, it's just a way to encode your image into a set of latent vectors and pass through a transformer network to generate a 3D triplane at a resolution of 64 by 64. The triplane features are then decoded into RGB colors and rendered using standard NeRF, rendering into multiple views for training. So here, this training using multiple views of NeRF, that's the score distillation training. TripoSR only learns the view-dependent colors and cannot model reflective objects. So TripoSR, which came out around 4 months ago, they did not have any material properties to them, which this paper does have. Several issues of the TripoSR and other similar networks are explained in the introduction, which we went over. SF3D overview. With SF3D, we propose several improvements to TripoSR to improve the output quality in different aspects. As illustrated in Figure 3, SF3D has 5 main components. And Figure 3, we'll go over that. It's right here after we're done reading this section. So as illustrated in Figure 3, SF3D has 5 main components. 1, an enhanced transformer network that predicts higher resolution triplanes. This helps in reducing aliasing artifacts. Top left in the figure, we'll see the figure later. 2, a material estimation network predicts material properties, which helps handle an object's reflective properties. 3, an illumination prediction. It's tackling illumination disentanglement, which helps out in outputting homogeneous objects without shadows and lets you do dynamic lighting. And 4, mesh extraction and refinement with the prediction of vertex offsets and surface normals, which helps in smoother output shapes. And let's with fewer mesh extraction artifacts. And 5, a fast UV unwrapping and export module that helps produce low poly meshes at high resolution textures. Next, we explain each of these modules in detail. So this is the table. Let me zoom out a bit for a second. So let's see. All right. So you have your input image, and it is sent into this Dino V2 encoder, and this Dino V2 encoder just turns it into a set of latent vectors, or a set of latent variables that efficiently store the semantic information of that image. And these triplane tokens, and that's turned into these triplane tokens. It's also combined with image tokens, and so this looks like what they're doing is similar to, or is the same as what they did in Trico SR, in which they will append the Dino V2 latent vectors with the camera extrinsic and intrinsic parameters. So these camera features being the rotation and translation of your camera, as well as the intrinsic parameters, which is things like the focal length and principal point. They didn't use. There's some important ones which I'm surprised they didn't use, which is I forgot the name of this parameter, but essentially it tells you the tilt of your sensor. And so the tilt of your sensor, if it's not perfectly orthogonal to the image to the plane you're taking a picture of, you could have some distortion. And so that's usually an important intrinsic, but I guess they didn't add it. All right, so let's move back. Give me 1 second. All right. So yeah, they get these image tokens and camera embeddings and triplane tokens, and they perform cross attention on them in this transformer. This gives you this triplane 3D4 by 3D4 representation. And before we move on, let's go to the bottom. They have this material net, which takes your input image and will output metallic and roughness values. They actually don't produce the values directly. They produce a distribution of the values, which they'll explain a little bit later. And so with this triplane, triplane representation over here, they're then able to produce the mesh through the density, which goes through demarching tetrahedra. Then they calculate some offset, some vertex offsets, which is kind of I guess you could say fine tuning of the demarching tetrahedra, which moves your vectors of your faces or your vertices in a way that is just a little bit nicer. These are just offsets or deltas. And then this is calculating by normal over here. I actually didn't get too much clarification. I assume they mean your normal vector, which tells you the direction in which light is supposed to reflect. But they didn't really explain what they meant by normal. And I was a little bit surprised to see it over here. And so this triplane also goes into this light net, and the light net produces this spherical Gaussian illumination. And I mean, we'll get into it later, but just to give you a little preview, how they're getting this representation of light is they're using these things called spherical Gaussians, and so essentially they're able to model the intensity of light at any given direction. But we'll get into more of this later. And they also use albedo to calculate this UV unwrapping, and now that you have a UV unwrapping as well as your mesh, you have a full mesh together, or a full object that you could use in games. And then figure 4 triplane resolution aliasing, we didn't go over that earlier. We found that low resolution triplanes struggle with high frequency and high contrast textures and produce grid-like aliasing artifacts. Our method increases the triplane size from 64 squared to 3D4 squared, allowing our method to reproduce these textures with fewer artifacts. So quickly, what they're saying is that with their triplane representation in the past, they did not have the capacity to express maybe some high frequency details or details that change very fast. And so if you just they found that just increasing the size of the triplane or the size of the representation, they're then able to show, for example, very fast hills and valleys or other high frequency details. And that's not necessarily just for color, although they mention over here for aliasing artifacts, which has to do with jagged edges. But this could also help express high frequency color color information as well. All right, so yeah, now we went over that. Let's go into this next section, enhanced transformer. All right, so first, as illustrated in Figure 3, we transitioned from Dyno using TripoSR to the improved Dyno V2, and both of these are just image encoders. So they turn an image into a set of or into a latent vector to hold the semantic information in a way that can be processed in another network. In this case, a transformer network. To obtain the image tokens for the transformer, we observed that low resolution 64 by 64 triplanes used in TripoSR and other networks introduce noticeable artifacts, especially in scenarios with high frequency detail, high frequency and high contrast texture patterns. Figure 4 middle, which you just went over, illustrates these aliasing artifacts. The triplane resolution is directly correlated with the presence of these artifacts, which you identify as an aliasing issue that can be mitigated by increasing the resolution. The increased capacity also improves the geometry. So that's just as we were going over. Naively increasing the triplane resolution quadratically increases the transformer complexity. We take inspiration. So what they're saying is that increasing the triplane resolution from I believe they had 64 squared to 3D4 squared would increase their computation quadratically. And this is a naive, and that's through the naive way of just increasing resolution. We take they go on to say we take inspiration from the recent point infinity work and propose an enhanced transformer network that outputs higher resolution triplanes. Point infinity proposes an architecture where the complexity remains linear concerning the input size by avoiding the self-attention on the higher resolution triplane tokens. With this addition, we produce 96 by 96 resolution triplanes with 1024 channels. We further increase the triplane resolution by shuffling the output features across dimensions, resulting in 40 channel features at 3D4 by 3D4 resolution. Further details about the architecture are available in the supplements, Figure 4. We'll go through the supplements in just a moment. I will have to be right back for just a second, but I'll be back in about, what time are we now? 3:54. I'll be back in about 1 minute. Be right back. All right. Sorry about that. I'm back. All right. So where were we at? Okay. I believe. Yeah. Okay. So we were talking about the high resolution triplane. So just to go over it quickly again, because I kind of lost my train of thought. These these triplanes. Well, first the attention. The transformer produces 96 by 96 resolution triplanes with 1024 channels. And they say they further increase the triplane resolution by shuffling the output features across dimensions. Now, they don't exactly explain what they mean by shuffling the output features, and what confused me even more is that this 96 by 96 times 1024. If we pull up a calculator real quick, calculator, or actually is there? Yeah, calculator. This 96 times 96 times 1024 equals this number over here, which is not the same as 384 times 384 times 40. So they result with into a different number of parameters. So they're not just reshaping the triplane, but they're applying some other function to it. And so if we go into their supplement all the way down here, they say, all right, enhanced transformer. To reduce the aliasing artifacts, we upgraded the transformer backbone to produce triplanes at a resolution of 384 by 384. All right, this is a repeat of what we read. All right, they say, inspired by the point infinity, we leverage a two-string transformer, which has a linear complexity with respect to the number of tokens, as illustrated in figure A1. Our architecture consists of two processing streams, the triplane stream and the latent stream. The triplane stream consists of the raw triplane tokens to be processed in each two-stream unit. The latent stream fetches information from the triplane stream using cross attention and performs the main computation upon a set of constant-sized latent tokens. The latent stream then updates the triplane stream with the processed latent tokens. Our full architecture consists of 4 such two-string units. With this computationally detached design, our transformer is able to produce triplanes at a resolution of 96 by 96 with 1024 channels. To further increase the resolution and reduce aliasing, again, we integrated pixel shuffling operations, enhancing the triplane resolution from 384 by 384 with a feature dimension of 40. Actually, I am remembering right now, I did look over this before I started the stream. There is another paper that, if we go to 48, real-time single image and video super resolution using efficient subpixel convolutional neural networks. So they're using ConvNet to do upscaling. I haven't read this paper. I don't know exactly how they do it. But you can think of it just some function that takes your triplane and upscales it. And I haven't quite looked into this appendix too much, so I don't quite understand what they're doing. All I know is that it will output a triplane. Maybe by the time we read this whole thing, we'll get back to this and try to understand it better. All right. So where was I? Okay. Material estimation. To enhance the output mesh appearance of the reflective object, SF3D also outputs the material properties of metallic and roughness parameters. Ideally, one would like to estimate the spatial varying material properties So that is the material properties being different across different groups of faces. Material properties at 3D output locations, but this is an inherently challenging and ill-posed learning problem that requires many high-quality 3D data with spatially varying materials. To overcome these challenges, we propose simplifying the material estimation problem by estimating a single metallic and roughness value for the entire object. So we went over this in the beginning. There's only a single set of materials, in this case metallicness and roughness, which apply to the entire object and every one of its faces. Although this non-spatially varying material mainly applies to homogeneous objects, we find that it significantly improves the visual quality of our mesh prediction, specifically as illustrated in Figure 3. We propose material net that predicts the metallic and roughness values from the input image. For pre-training material net, we selected a subset of 3D objects with PBR material properties from the synthetic training dataset and rendered them under different illuminations and viewpoints. We observed that directly regressing the material values often leads to training collapse, where the network always predicts a roughness value of 0.5 and a metallic value of 0. So again, as they're saying that only training training to directly get the value of material and roughness they want leads them to having a training collapse. I'm not exactly sure as to why. I haven't thought about that too much, but empirically, that's what happens. As a remedy, we propose a probabilistic prediction approach, where we predict the parameters of a beta distribution and minimize the log likelihood during training. This applies to this stabilizes the training by allowing for uncertainty in this ambiguous material estimation task and prevents the collapse observed with direct regression. So just to show you guys what they're talking about, they predict this beta distribution over here. So it's not a single value, but they're instead, as we're saying, predict the parameters of this distribution. Where was I at? Whoops. Alright, okay. During inference and training of SF3D, we do not sample the distribution, but calculate the mode of the distribution. So they're not calculating, or they're not sampling randomly with respect to the probabilities, but instead they're just taking the highest point of this distribution and taking that as their value at all points, or at all inference times. We implement the material net by first passing the image through the frozen clip image encoder. So this is kind of like Dino, but a smaller network where it just getting a vector encoding of your semantics of your image through clip to extract semantically meaningful latents and pass them through 2 separate MLPs with 3 different layers and 512 width to output the parameters for the distribution. Illumination modeling. We propose explicitly estimating the illumination in the input image to account for varying shadings, example shadows. Otherwise, the 3D outputs would have baked in illumination effects into their RGB color. As illustrated in Figure 2, to this end, we propose a light net, Figure 3 bottom right, that predicts the spherical Gaussian illumination map from the estimated triplanes. So this is what like I was showing you guys earlier, they're predicting these spherical Gaussians that pretty much tell you the intensity and the intensity and radius, I guess you could say, or bounds of your light source, and they could use that to remove that. They could then use that spherical Gaussian map to remove um, predicted lighting parameters or predicted lighting effects from their lit 3D mesh, and so they'll result with a unlit 3D mesh. So the rationale here is that the triplanes encode the global structure and appearance of the input object and should account for the 3D spatial relationships and changes in illumination over the object surface. We use 96 by 96 resolution triplanes from the transformer and pass them through two convolutional neural network layers, followed by a max pool and a final MLP with 3 hidden layers and a feature dimension of 512 for all the layers. LightNet outputs the grayscale amplitude value for 24 spherical Gaussians. So the way I'm imagining this, if I understand it correctly, well, I closed the spherical Gaussian stuff, is pretty much think of that spherical Gaussian image I was showing you earlier, oriented in 24 different ways to show you so you can get a intensity of a light source from 24 different directions with a soft plus activation to ensure positive values. So that's just making sure that you don't have negative light. The axis and sharpness values for these spherical Gaussians remain fixed and are set up to cover the entire sphere. These amplitude values allow us to implement a deferred, physically based rendering approach similar to that used in Nerd. And I have not read Nerd, so I'm not exactly sure what the approach they're talking about is. Our method also incorporates a lighting demodulation loss during the training phase, inspired by the works of Hazelgren et al. And Folletti. This loss function ensures that the lighting on an object with an entirely white albedo closely matches the luminance of the input image. The demodulation loss enforces consistency between the learned illumination and the lighting conditions observed in the training data. This can be seen as a bias to resolve ambiguity between appearance and shading. So, right. So they're saying that the lighting on an object that with a entirely white albedo closely matches the luminance of the input image. Sorry, I don't exactly see what they're saying. This loss function ensures that the lighting on an object with an entirely white albedo closely matches the luminance of the input image. The demodulation loss enforces consistency between the learned illumination and the lighting conditions. So, okay, there just seems to be, to me, just a loss that is just a somewhat standard loss. I don't exactly know, or I don't exactly understand the construction of it. I thought I did, but we can could get back to that later. Okay, so 3.4 mesh extraction and refinement. Figure 3 top right, which is what we went over. I just see that we have a new viewer, so I'll show them. Top right over here. Whoops. Okay. Extraction and refinement. Figure 3 illustrates this module. We convert the estimated triplanes into a mesh using a differentiable marching tetrahedron. So that's the stuff from deep marching tetrahedra, dmtet, which I won't get into again, but just I guess I will get into it again. It's a grid of tetrahedra, which can be used to encode encode a discretized isosurface or sign distance field. And this deep marching tetrahedra is a way of producing a mesh entirely differentially, so that you could backpropagate through the mesh instead of having to do some optimization on a higher or lower level representation of your 3D object, such as a sign distance field. And also, this is better than some of their previous approaches that use they use either cube grids, they use cube or pyramid grids, because this, well, one, it's shown empirically, and two, they allow for a dynamic resizing or deformable tetrahedral grid, and that in places where there's high resolution or high frequency details, it'll naturally divide the grid into sub-tetrahedra until it has a desired resolution. So it's kind of like hierarchical voxel grids, but in this case it's a tetrahedral grid instead of voxels. As explained, all right. As explained in the introduction, marching cubes usually results in several staircase artifacts, that being jagged edges, on the resulting meshes. We propose two new MLP heads to refine the meshes as a remedy. One predicts the vertex offsets, and another one predicts the world space vertex normals. So these vertex offsets, they're just calculating like a delta in which it'll be applied to this to the result of the demarching tetrahedra, and so you can move each vertice of your object in a specific small amount, which will result in a smoother surface with less staircase artifacts or jagged edges. And another one predicts the world space vertex normals. This I don't exactly see what they're doing with the vertex normals. Maybe I forgot it because I read this a little while ago. But I guess we'll see when it comes up. Inspired by Mesh LRM, we also implemented small split decoder MLPs for these two networks, which proved beneficial for performance and efficiency. We found that the vertex offsets can reduce artifacts from the tetrahedral grid, and the world space normals can add details to the flat mesh triangles. Okay, but how exactly is this adding detail to the flat mesh triangles? Maybe I just don't know enough about world space normals. If someone in the chat wants to, or someone wants to write in chat how exactly it's doing this, that'd be appreciated. Given that the normal predictions are initially unreliable, we stabilize the training by using spherical linear interpolation, SLIRP, between the geometry normals and in R3 and our predictions. This SLIRP is used during the initial 5,000 training steps. To regularize the mesh estimation, we use several training losses: a normal consistency loss, a Laplacian smoothness loss, as implemented by 3 Studio. This is just it's a GitHub repo that has implementations of a lot of 3D generative models, and a vertex offset regularization for supervising the normal prediction. For supervising the normal prediction, we use a geometry normal replication loss. And again, I still don't understand quite what the normal prediction is doing. We use a geometry normal replication loss. L normal replication equals 1 minus the ground truth normal dot the predicted normal, where dot is the dot product, and a normal smoothness loss to ensure the smoothness of normal predictions in 3D. This loss is achieved by adding a small offset epsilon in R3 around a query location x in R3. The loss is then defined as L NRM smooth is equal to n hat or n predicted of x minus n predicted of x plus epsilon squared. So this is another regularization term, which seems to be, if I understand this correctly, they're just trying to make sure that the normal prediction won't change at extremely high speeds, or in other words, it's reducing the derivative. And I still don't exactly know how the normal normal vector is affecting the object, but it seems to have something to do with having less, I guess you could say, jagged edges in this normal space. So 3.5, fast UV unwrapping and export. The final stage of SF3D is an export pipeline that outputs the final 3D mesh along with the corresponding UV atlas. So if you guys aren't familiar, in order to have color on a mesh, you need to have what's called a UV atlas, and this UV atlas just defines a bunch of colors. Is the easiest way of putting it, and you can associate each vertex in your object to a coordinate on this atlas, which then gives that vertex a color, and the color of your face, your entire face, will be an interpolation or a blend of the vertices that comprise the face. So if it's a triangle, you have your three vertices with, and each vertex has one color, and the color of your face is an interpolation across the colors, or across the vertex colors. An overview of these stages is provided in Figure 5, where we do fast UV. Oh wait, I think I skipped a part. Yeah, our export pipeline follows multiple stages to ensure efficient and effective handling of 3D models. An overview of these stages is provided in Figure 5, where we first do fast UV unwrapping. We then bake the world's position and occupancy to the UV atlas, which we use for querying the albedo and normal. An overview of these stages provided in Figure 5. Where's Figure 5? Our export process starts with the mesh and is followed by UV unwrapping, occupancy, and world's position baking, material querying, and UV island margins. So this gets into more detail in a bit, but they have this color they have this mesh and color, and they're projecting, or they're unwrapping this these colors into an atlas, and they have this UV occupancy plus position and material query, and we'll get into this in more detail in a little bit. So where were we at? So an overview of these stages is provided in Figure 5, where we first do fast UV unwrapping. We then bake the world's positions and occupancy to the UV atlas, which we then use for querying the albedo and the normal. So the albedo, that's just the color. The normal, I mean, I haven't seen anything where normals are queried. Usually, like how an OBJ file is defined, you'll have your definitions of each of your faces, and it's explicitly set that you have a normal direction. In other words, the direction that light is reflected off your surface, like closely defined with it. So I'm not quite understanding what they mean by querying the normal. Anyways, this results in the final textured 3D mesh. The entire export process only takes 150 milliseconds, which is pretty fast. UV unwrapping is traditionally a computationally intensive process. Existing methods require several seconds for UV unwrapping, which is impractical when we are aiming for sub-second generation speeds. To address this inefficiency, we propose a cube projection-based unwrapping method. The key advantage of this approach is it is parallelizable. So kind of like how transformers are super fast, not necessarily because they have a low order, a low like O of n or O of n squared. So what I'm trying to say is that transformers, for example, they have they're computationally inefficient in that computation increases quadratically, but because all the attention mechanisms is parallelizable, it's still faster than, for example, RNNs, which have to be done sequentially, and is not parallelizable at all. Each face of the mesh can independently decide which cube face to project onto based on its surface normal. Our UV unwrapping process is illustrated in Figure 6. We initially align the output mesh based on the, yeah, we'll see Figure 6 in a second. We initially align the output mesh based on the most dominant axes with cube projection coordinate system. After each mesh face selects the appropriate cube direction, we address potential occlusions. Without managing occlusions, and occlusions, in other words, meaning places on your atlas that maybe two faces project onto at the same place. So it's a single place that more than one face projects to, and so you need to handle that. Without managing occlusions, different faces can share the same UV coordinates, leading to artifacts in the texture. We detect occlusions in the UV atlas by performing a 2D triangle intersection test. And so I don't exactly know what this is, but it sounds like it's just a basic algorithm that will take triangles and just check if they're intersecting. And if they are, then they're occluding, and you need to handle that. We filter triangles by their proximity to the triangle centers to make the process efficient. So they're only doing these triangle intersection tests if it's within a certain distance from the center of a triangle. If an intersection is detected, we sort the intersecting triangles based on their depth in the plane, keeping the first intersection depth in the plane, keeping the first intersection and marking the others for reassignments to different UV atlas areas. So you have your UV atlas. Let's say two images project to the same place, and depending on which one has a higher depth order, the one with I believe it's the lowest depth order, will stay in the place it's projected to, and the other occluded faces will be moved to some other place in the atlas. So this is like another geographic location on this atlas made of pixels, or not necessarily pixels, but colors. Okay. Marking the others for reassignment to different UV atlas areas. The first intersection is placed in the top third of the UV atlas. The second intersection is placed in the bottom left area, and the remaining triangles are organized into a grid in the bottom right section of the atlas. So you could kind of see here, actually I don't know if this is showing what I think it's showing. Where the map services. Okay, so this is Figure 6, which I believe we talked about over here. Yeah, so Figure 6 is a summary of what we were just talking about. So UV unwrapping, our UV unwrapping technique uses projection wrapping, so it's projecting the object to a 2D surface, allowing each face to independently select a projection, enabling easy parallelization. A naive approach could lead to the same UV coordinates being assigned to different vertices due to occlusions. We identify potential overlaps from occlusions on the 2D map surfaces and relocate them to different areas within the UV atlas. Any remaining areas are placed in the bottom right of the UV atlas. This method minimizes distortion and ensures most surfaces are preserved in a connected area. So this is their UV atlas, and this bottom right area is when you have more than 3 occlusions on a single cubic area or square area in your atlas, and this is another place for, I think this is second order occlusions. No, this is first occlusion, and I don't think they're showing the second occlusion, and your final remaining occlusions go and they're just these grids over here. They then say we also rotate each island to minimize the shading scene. I think I skipped a part actually. The first intersection. Okay, no, I didn't. We also rotate each island to minimize the shading seams by following radial Z tangential orientation. Now, what they mean here is that on your atlas, you'll have it's kind of organized into multiple blobs of colors, um, and sometimes, or most of the time, your 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 vertex colors are in similar position in like similar geographic areas, uh, like the actual vertices in your or they're distributed in a similar way to your actual vertices in your object. And so if you have a lot of high frequency details or colors that change very fast in the same area, you might end up with some artifacts of like immediate splits between colors. And so what they do is that they're rotating these blobs in such a way that the derivative of the color or the speed at which the color changes between these blobs are minimized. And so this reduces your amount of what am I looking for? Artifacts or like splits. We then assign each face to a position in the UV atlas as defined in Figure 6. Right. So it looks like what they're doing here. They're not individually going for each vertice and saying your vertex color is this position on the atlas. It's taking the entire face and pushing that face onto your atlas, and wherever those vertices land is the vertex color. And so that's why it's necessary to have that geographic smoothness. Next, we bake the world positions and the occupancy data with UV unwrapping into the final UV atlas. We bake the world position. Okay, this, to be honest, I don't quite get this stuff. Anyways, this allows us to query the world positions within the chart from our triplanes and decode the albedo and surface normals into additional textures. We transform the world space normal map into a tangent space normal map using the tangent and bit tangent vectors. We then add margins to the UV atlases to prevent visible seams at UV island borders. So this is like what I was saying earlier. In addition to doing this radial Z tangent orientation rotation, they're also applying margins to each of these, I guess you could say, blobs of atlas, so that it doesn't change color immediately. Okay. Where was I at? What the I lost where I was. Okay, we add margins to the UV atlases to prevent visible seams at UV island borders. This is achieved through an iterative process. In each iteration, we perform a 3x3 partial convolution based on the occupied areas using the valid regions of the kernel. We then use a 3x3 max pooling operation to expand the occupied regions of the UV atlas, placing the mean values of the newly expanded areas while preserving the original regions. This iterative extension ensures that the texture smoothly blends outward. So, I guess a way of summarizing how they're doing it is that you'll have this atlas, which is like a 2D surface, and they're separating it out and then filling in the blank with a mean value of the region around it. Okay. Placing the mean values on the, okay. This iterative extension ensures that the textures smoothly blend outwards. We incorporate our image estimators, metallic and roughness values, and pack everything into a GLB file, ready for efficient rendering and use in various applications. So, alright, we're almost done. 3.6, overall training and loss functions. Directly training our method with mesh rendering yielded unsatisfactory results, hence we pre-trained it on the nerf task. Following this pre-training, we transitioned to mesh training, really quickly, this nerf task they're talking about is if you're not familiar with nerf essentially will take a position and orientation um, of your camera and will tell you what you should see. So it'll predict for each pixel of that camera um, what the color of that pixel should be. So it doesn't have an actual physical it doesn't have an actual physical object, but the object is kind of implicitly stored in an NLP, otherwise the nerf, and that NLP will tell you what you should be seeing at any particular position. So they pre-train on that first. Following this pre-training, we transition to mesh training, replacing the nerf rendering with differentiable mesh rendering. This is the deep marching tetrahedra, and spherical Gaussian-based shading. Given the introduction of light estimation, we found that using larger batch sizes aids convergence. We initiate training with a batch size of 192 and a rendering resolution of 128 by 128 training for 10,000 steps. In the subsequent stage, we reduce the batch size to 128 and increase the resolution to 256 by 256, continuing for another 20,000 steps. This stage involves 80,000 steps at 512 by 512 with a batch size of 96. Now, the loss function remains consistent across all mesh training stages. We primarily use image-based metrics. So this is like score distillation sampling, where they're comparing your rendering of your object compared to a ground truth image of your object, and that's your loss, where you're trying to minimize the difference between your ground truth and your rendering of what you have. To compare our rendered and shaded reconstructions, I had with the ground truth image I. These include mean squared error loss and LPIPs. I'm not familiar with LPIPs. We also incorporate a mask loss between the ground truth mask and mask M and the predicted opacity M. Where do they predict opacity? I don't quite remember them predicting opacity. I'll do a Control F search for it in a bit. Defined as a mean squared error loss. We then define 3 loss formulations for the rendering, mesh regularization, and shading. Okay, so loss of render is mean squared error. Lambda, we have 2 mean squared errors. I believe one of them is was explained earlier. Anyways, a lambda mean squared error. This other loss mean squared error that was just defined here. LPIPs, which I'm not familiar. Oh, okay, sorry. So they're multiplying their mean squared error by a percentage of that mean squared error. In this case, it's 10. I'm not particular why that's the case. So this would result in being mean squared error squared times lambda. I'm not exactly sure why did they do this, but that's what they do. Plus this LPIPs, and then plus this lambda mask times mask loss. And then they have their mesh loss, which is the Laplacians plus the normal consistency plus the offsets. Just for brevity's sake, I'm not going to keep repeating the terms. And then there's loss of shading, which is the loss of mesh. Is this loss of mesh? Okay, they put a minus sign here instead of an equal, so kind of confused me for a second. So this loss of shading is equal to the normal replication plus normal smooth, times normal smooth, plus the demodulation loss. So the total loss that we're back propagating from is the loss of render plus loss of mesh plus loss of shading. Now, finally, results. I haven't actually read the results yet. I was kind of in a rush. So data sets. For comparison, we select GSO and our Omni Object 3D as our primary data set for evaluation. We select 278 random scenes from GSO and 308 scenes from OmniObject 3D. For comparison, we render 16 views. Sorry, one second. We render 16 views around the object and select a frontal as the conditioning view. Baselines. Okay, select a frontal as conditioning view. Baselines. We compare with several recent methods for fast 3D object reconstruction from a single image. We mainly focus on the fast reconstruction models to maintain a consistent evaluation protocol across different techniques. We also mainly consider meshes as outputs and perform the evaluations on the mesh, which makes sense. I could see some of these other papers which maybe produce a 3D Gaussian splat or a NERF or ISO surface, maybe saying, well, they would have performed better if you did your comparison on their output, but you know, eventually the mesh is what we need anyway, so it makes more sense to do what they're doing and compare against your meshes. We use the official implementation for all the baselines, and we evaluate all the methods under the same protocol. We selected several recent and concurrent works with source code releases for comparisons. Specifically, we compare against OpenLRM, Tripo SR, LGM, CRM, Instant Mesh, and Jesus Christ, and Zero Shape. For OpenLRM, we selected the large OB-Objaverse 1.1 model. We use H100 GPUs for comparison. And so over here, yeah, we can see if I zoom in a bit here. There's the output. So hold on. So there's the input and your ground truth. I don't see. Okay, so this is the input image of your ground truth. This is the actual model of your ground truth. CRM produces this. LGM, these are all the productions across different I'm looking for models. And okay, so Tripo SR, which is what this paper is building off of, you can tell, especially with their lighting materials, is that we have more of a glare over here, and so you can see that there's a little bit of glare on Tripo SR, but this seems to me to be more of a fact of having lighting artifacts within the object. So it has the light actually within its UV atlas instead of predicting how light would reflect off its color like this one over here, or off the object. I'll be 1 second. All right, sorry about that, but we're back now. Okay, so what were we looking at? Oh yeah, we were looking at the comparisons across different models. All right, and then they have their actual scores, the numbers to see. And here, let's read this. Table 1. Comparison on 3D metrics demonstrating state-of-the-art performance of SF3D. it's worth pointing out that all other methods produce meshes. Sorry about that. That's the doorbell. Produce meshes with drastically higher polygon counts. This allows them to follow the surfaces more closely than our low polygon meshes. Our meshes can outperform the others by using our learned vertex offsets, and our method is also one of the fastest to generate a mesh from an image due to our efficient extraction pipeline. So really quick, they're saying that since they have such high, since these other models have such high vertice count or face count, they're able to model these smoother surfaces, or they're able to align closer to the ground truth surface because they have the capacity to hold all that information within all these vertices, and they have a model producing all this. While with SF3D, they have a lower vertice count, and so you'll end up with more jagged edges just as a result of the way that they produce these meshes. But having these vertex offsets they have, that they're able to push these vertices in a certain way that makes it smoother and align closer to the ground truth mesh. And so I'm not actually too familiar with these loss metrics, or these I guess they'd be loss metrics. But GSO on the object, let's see. So there's their time. This one clearly has the lowest. You have Tripo SR. Tripo SR has the lowest at 0.3, and SF3D at 0.5. So that's kind of interesting. Tripo SR, the paper that this is based off of, is doing better than SF3D, but I guess it doesn't have this vertex offset or color disentanglement or material prediction. So for only 2 milliseconds, or I believe that's 2 milliseconds, it gets a lot faster. And then there's all these other metrics which I'm not familiar with. I can interpret for you. All right, evaluations. For runtime comparison, or actually we also have this over here. So table 2, ablation. As our model builds upon Tripo SR, we use it as our baseline. Without our enhanced transformer, our mesh training has already improved upon it. With our architectural improvements, we outperform the baseline significantly. So, yeah, all I can tell you is that all I can tell you is that there's higher numbers here than there's for Tripo SR, and so this seems to be it's better. Okay. For runtime, I'm just gonna be 1 second. I'm just putting this laptop on a charger. It's about to run out of battery. All right. Evaluation. For runtime performance, we consider the meshes as the final output and calculate the entire runtime required to go from the input image to the final mesh. So they're also not, well, actually, never mind. I was going to say that they're not talking about the fact that it doesn't go straight from text to object, but neither does any of the other models, I believe. So it doesn't matter. We then perform separate evaluations for their shape quality. Several models cannot be conditioned on intrinsic and extrinsic camera parameters, so we propose performing an alignment step. So they're saying that some of their models aren't parameterized on like the position and rotation of the camera, as well as its intrinsics like the focal length and like sensor tilt. And so they're doing this alignment test, this alignment step. Where was I? So we propose performing an alignment step. We normalize the mesh, perform brute force rotation alignment tests, and select the rotation with the lowest chamfer distance CD. So it looks like what they're doing is they're rotating the mesh in a bunch of different ways and getting a rendering of that, and whichever has the best score of producing the object is what they use as the chamfer distance, which I guess is some metric to evaluate quality. We then run another alignment step using iterative closet point, where we further optimize the rotation and translation. We then calculate the standard shape metrics of chamfer distance and f-scores after this alignment. This alignment might still misalign symmetric objects for re-rendering. This alignment might still misalign the symmetric objects for rendering. Hence, we only report indicative rendering metrics in the supplements. Okay. All right. Triangle counts. We run each method under the default configuration, as the triangle count varies drastically based on the 3D mesh. We report the triangle count for a single mesh here, instant mesh 50 for single mesh here. For instant mesh, there's 57,000, CRM 24,000, LGM 42, Tripo 32, OpenLRM 662, and for SF3D, there's only 27,000, which is quite an improvement over Tripo SR. Okay, results. In table 1, we compare our, so I believe we looked at that already. I think this is table 1. In table 1, we compare our method with all the baselines. Here our methods outperform all current and concurrent baselines on both chamfer distance and f-scores. This indicates that our method can reconstruct accurate shapes even if our models have fewer polygons than other baselines. From the visual comparison in Figure 7, it can be seen that the accurate shape reconstruction of SF3D also translates well into the visual quality of, let me actually close this OBS, of other 3D assets. Here it is worth noting that SF3D also handles fine geometry like the glass as well. So they're talking about over here. The shape also translates well into the visual quality of the 3D assets. Here it is, also handles fine geometry like the glass as well and produces consistent shapes with more detailed textures than state-of-the-art methods. Moreover, the result also shows sensible material properties and albedo as seen in Figure 8. This Figure 8 over here? Yeah, Figure 8. Decomposition results. Here we use high-quality objects from Polyhaven and render them under natural illumination. These illuminations are highly challenging for material estimation. Still, our model estimates sensible material properties which allow for convincing relighting. So if I zoom in here, I believe that is the material properties. Not material properties. Maybe material properties. Actually, I'm not sure. What am I looking at? Okay, the diffuse. Okay, the thing that's kind of getting to me is we don't actually predict diffuse, or at least they didn't say it. They said that they predict the roughness and metallicness, but not the diffuse material. So ground truth hours. Okay. Okay. Well, I guess yeah. Over here we can see diffuse is flat, so I guess it's using some default number. But for roughness metallic, what am I looking at here? It's kind of hard to interpret what they're saying. Let me reread that for a second. Here we use high quality objects from Polyhaven and render them under natural illumination. These illuminations are highly challenging for material estimation, so our model estimates sensible material properties. Okay, so it's just what's it called? It is just lighting them and only displaying the light or the effect of certain material properties. And I guess this is supposed to show that this has convincing results. Okay, where were we at? Figure 8. Over the results, okay. This is a highly challenging as objects are only rendered under natural illumination. Estimating material properties without any knowledge about the illumination is a highly ambiguous problem. Now, inference speed versus reconstruction quality. In Figure 3, we plot the inference speed versus reconstruction quality for different techniques. The best performing methods should be located on the top left corner. While our method is slightly slower than Tripo SR, the reconstruction accuracy is considerably better for SF3D. It is also worth noting that our reconstruction has smoother shading with less pronounced marching cubes artifacts, as seen in Figure 7. The final apparent asset quality is thus even higher for our method. Okay, so you guys might be hearing some stuff in the background. I do live in a shared household, so I can't really take up the entire audio bandwidth, if that's a way to put it. Okay, the best performing methods should be located in the top left corner. Okay, let's go see Figure 9 now. So inference time in image/seconds. Figure 9, image to mesh time. So image to mesh time versus reconstruction quality. Our method is not only one of the fastest reconstruction methods, it is also capable of producing highly accurate geometry. So you have their f-score, which I assume is their quality, and inference time in image per second. Okay, so you can already see the highest quality goes to TricoSR, and inference time is also the lowest, all the way to the left. So it's super high quality, and it's nearly it takes nearly the lowest time, or it's the second fastest model, only beaten by TricoSR, its predecessor. So ablations, we evaluate our additions. So I think I kind of looked possibly at some of these tables in an incorrect order, but it's alright. Ablations, we evaluate our addition in table 2 against baseline models. Our method is built upon TricoSR, so we use it as our initial baseline. If we add mesh training and relighting as a fine-tuning step, we can see that SF3D without enhanced transformer already improves upon TricoSR, demonstrating the use of our mesh-based rendering. This improvement is mainly due to the efficient rendering, enabling higher resolution supervision during training and smoother meshes from vertex offsets. If we add our high resolution triplanes using our enhanced transformer, SF3D further outperforms the baseline considerably. Alright, limitations and outlook. As seen in Figure 7, top row. Alright, let's get back here. As seen in Figure 7, top row, the cup's albedo is not perfectly matched. This is related to the LDR output, where the dark spots do not contain any useful information. LDR, it's related to the LDR output. The light, I think this has to do with the light net, or the light map. LDR output, or LDR input. Let me just, 1 second. LDR. Okay, LDR is said once. I forget what LDR stands for. Where the dark spots do not contain any useful information. Furthermore, roughness and metallic properties are homogeneous, which limits their usefulness for objects containing multiple drastically different materials that are spatially varying. In addition, our method also introduces material predictions and delighting without explicit supervision. Let me just reread that. My mind just completely lost train of thought. In addition to our method also introduces material prediction and delighting without explicit supervision, as we do not require explicit supervision of these parameters. Our method could be extended to train on real-world data sets, which we leave for future work. Similarly, the UV unwrapping could leverage existing data sets for further improvement. So yeah, this LDR, it stands for light something reconstruction. I forgot what the D stands for. Oh, light delighting reconstruction. I think that's what it stands for. I know there's delighting reconstruction. Anyways, the UV unwrapping, yeah. So our method can be extended to train on real-world data sets, which we need for future work. Similarly, the UV unwrapping can leverage existing data sets for further improvements. So finally, the conclusion. We present SF3D, a fast single view to UV unwrap texture object reconstruction method. In addition to our fast extraction pipeline, we introduce several architectural improvements to feed-forward-based 3D reconstruction methods, which help our model produce highly detailed geometry and texture. In our extensive evaluation, we show that our method outperforms existing and concurrent baselines in both speed and quality. All right, that is the entire paper. If there's any questions that I could perhaps answer, let me know. Let me pull the chat up. In this laptop over here. But if there's no questions, I will say I just started a Discord server. So go to my bio on Twitter. You can join it. There are no YouTube watchers, so there's no one to tell them over there. But you 7 people on Twitter. You can join my my Discord server. I'm trying to build a community. I'll be doing more of these streams. This is my first one, so it wasn't the highest quality. I don't think I prepped well enough, but it's all right. We always got the next ones. But yeah, right now it's 4:57. At 5, I will be ending the stream. But if anyone wants to type in chat, ask anything, then go ahead. But I guess we could go over again this supplementary material that I kind of glossed over and didn't really get. So to reduce the aliasing effect, we upgrade the transformer backbone to produce triplanes at a resolution of 3D4 by 3D4. By the way, if anyone wants to clear this up for me, I mean, I know this paper came out yesterday, so there's probably not that many people that know it intimately. But if any of you do know it or understand this better, please let me know. So, however, naively increasing the triplane tokens in Triple SR is computationally prohibitive due to the quadratic complexity of self-attention inspired by points infinity. We leverage a 2-stream transformer which has linear complexity with respect to the number of tokens, as illustrated in Figure 1 or Figure A1. Our architecture consists of 2 processing streams: the triplane stream and the latent stream. The triplane stream consists of the raw triplane tokens, okay, to be processed. Each 2-stream unit, gray box in A1. Okay. So this is ln plus fc. What is ln? Is ln supposed to be linear plus fully connected? But a linear is fully connected, so I don't I don't know what ln is. To be processed in each 2-stream unit, gray box in Figure A1, the latent stream fetches information from the triplane stream using cross-attention. Okay, so it's doing some transformation to your triplane token and some transformation to this conditional token C. It's performing cross-attention on them. All right. Where was I at? The latent stream and triplane stream using cross-attention and performs the main computation upon a set of constant size latent tokens. The latent stream then updates the triplane stream, the processed latent tokens. The latent stream updates the triplane stream of the processed latent tokens. Our full architecture consists of 4 such 2-stream units. 4 such 2-stream units. With this computationally detached design, our transformer is able to produce triplanes at a resolution of 96 by 96 by 1024. To further increase the resolution, they do pixel shuffling. Okay, I didn't read this part. For image metrics, we follow the pipeline of the shape metric calculation. We further scale the normalized objects back to, right, this is a separate thing. Okay, so let me read over here. Figure A1, enhanced transformer architecture. Our new backbone produces higher resolution output triplanes. We further upscale them using a pixel shuffle. This helps capture high frequency, high contrast textures with a reduced aliasing figure 4. So they have some fuse block, some compute block, and some other fuse block. I don't know what these are. Are they concatenating the triplane stream with this cross attention output? Oh, Jesus! It says right here. So LN. What the hell is LN? Uh, LN. I'm just searching for. Yeah. Okay. So layer norm, bro. I had this too zoomed in. LN equals layer norm. FC fully connected. All right. So it does layer norm. There's I don't know if it's doing layer norm before doing this fully connected, but I think so. So they do some normalization, and they do a linear or a nonlinear transformation through this fully connected layer, and this fuse block takes will take your triplane token, do a layer norm on it, and we'll do cross attention with KV. In this case, KV being, KV is your triplane token, and what goes through the layer norm is the result of C. Oh, C is concat, not cross. Okay, so they can cat these two together, and they normalize it, and they'll perform cross attention with the result of this layer normed and fully connected triplane token, and then plus they'll add that back to the projection, or the concatenation of the projections of this conditional token and initial token. They'll add those together, so it's kind of like a skip connection. If you guys are familiar with ResNets, and they'll put that through another layer norm and fully connected layer, and they will add that again to what was before the layer norm and fully connected. So that's another skip connection. And then they'll put that through what's called a compute block, which will do layer norm, self-attention, and then a skip connection with itself before layer norm, and then do another layer norm cross-attention with the result of the layer norm and the conditional token, then do another skip connection, and then do layer norm plus fully connected plus another skip connection, and they do that back into a fuse block. They do that 3 times. Then they put it through a fuse block again, and they put the output of the compute blocks and this fuse block into a fully connected network, which is then your new triplane, if I understand correctly. Okay, I think I'm beginning to understand this. Okay, I still don't understand with the triplane token. I don't know where they're getting this conditional token from. Is this just something else we're conditioning on? Let's see. Jesus Christ. Appendix. No? I thought we're talking about the appendix somewhere. Okay, enhanced transformer, especially in scenarios of. Okay, so naively increasing the triplane resolution quadratically increases the transformer complexity. Take inspiration from the recent point infinity work and propose an enhanced transformer network that outputs higher resolution triplanes. Point infinity proposes an architecture where the complexity remains linear. Yeah, okay. You produce 96.96 resolution triplanes. Okay, but they're not talking about this this conditional token though. Maybe they clarified it here and I just forgot. By point infinity, we leverage a 2-stream transformer, which has our architecture consists of 2 processing streams, the triplane stream and the latent stream. So Okay, hold on. The triplane stream consists of 2 raw triplane tokens to be processed. In each 2-stream unit, the latent stream fetches information from the triplane stream. Using cross-attention, performs the main computation. The latent stream. The latent stream then updates the triplane stream with the processed latent tokens. So I'm kind of, maybe this conditional token is learned or something. I'm not sure what they're initializing this from. Anyways, I think to get a better understanding of this, I'll have to go through this point infinity. But apart from that, this stream, I guess, is over. I went through the paper. Yeah, that's everything good. All right, you guys can join my Discord if you'd like. I'd like it. Yeah, that's everything. I will be streaming again. I don't have a specific day in mind, but sometime in the near future. Actually, I am building a startup with a friend of mine, and I'll be streaming our progress probably daily or a couple times a week.